EDU-ARCTIC 2, Polar Research for Education, innovative program in Poland and Norway. Webinars.
I will talk about life of the glaciers, how they are formed, if they can be considered as a habitat, and how, well, basically how all this system works. If you have any questions during the presentation, just please ask. I see no problem with that. So, first of all, what is the glacier? Well, basically, we can tell that glaciers are kind of rivers made of ice. Very often, they have a form of a kind of river, which is built of ice crystals, snow, and material within. So they are like rivers. Sometimes they are a bit different, but I'll talk about this a bit later on. There's about 200,000 glaciers in the world, which might be surprising for many people, as we think that glaciers are only in the Arctic, Antarctica, and in high mountains, but there's quite a lot of high mountains in the world. Only continent without glaciers is Australia. Even in Oceania, there's a bit of glaciers. Area with most of the glaciers is north, like the Arctic, but also Antarctica. There are glaciers both in South America and North America. There's a lot of glaciers, about two large ice caps, the Greenland ice cap and Antarctic ice cap. But also in Asia, we get a lot of glaciers in Asia. And there's, hopefully you can see that, but there are also really tiny glaciers still in Africa. And hopefully they will stay with us for a little longer than glaciers in Europe, like in Spain, France, basically Alps and Dolomites and Pyrenees. As I said, there are different types of glaciers, but we can share them into two basic types. And one of them is this further mentioned alpine glaciers, rivers of ice. Here on the left side, you can see one of such glaciers in the Alps, and the other one are ice sheets, which are big chunks of glacier ice, and they can be size of continent like Antarctica, or they can be like 20 kilometers wide, depending on location. There are two big ice sheets in the world. First one is Antarctica, the other one is Greenland, but there's quite a lot of over ice sheets like Patagonian ice field or big ice sheets in Alaska or tiny ice sheets in Svalbard. And how they are formed. First of all, to have a glacier, we need snow. Glaciers are formed with snow. They start with falling snow, and when the snow is accumulated layer by layer, like in the winter time, if it happens that this snow will persist to the next winter and another winter, the ice crystals in the snow will transform. First, they will transform to firn, which is porous ice form. Those are like bigger ice crystals that there's quite a lot of air trapped between the firn crystals, and they are formed at the depth of 5, 10, 25 meters. And then when you still have like falling snow from year to year, the mass builds up on the top, and the ice crystals are squeezed more and more and more and more, and they start transforming to glacier ice. So in the glacier ice, we can have air, like you can see on the left side. We can have air that was trapped thousands of years ago. Yeah, and that's basically how they are formed. But to have them formed, we need to have like specific conditions. So the temperatures has to be low, and there has to be enough precipitation. If there won't be any precipitation, or it's gonna be like very dry areas, then we won't have glaciers there. There are places in Antarctica which are called dry deserts, and it's cold enough, but it's also too dry. There's not enough precipitation, and glaciers do not form there. Very often we call them oases. They can be they form locally. They can be encapsulated by ice caps all around, but still locally it's too dry for precipitation there, and glaciers won't form there. So, as I said, I mentioned accumulation and ablation. Those are two processes that run the glaciers. In most cases, like when we think about glaciers, those are mountain glaciers, so they have to be high up enough that it's cold, and as I said, snow will persist to the next season. And process of accumulation means that snow accumulates. It starts in late autumn and then stays till, depending on the area, till January, even March, sometimes in the Arctic, even April or beginning of May, snow accumulates, which means it's constant snowfall. Snow is falling and falling and falling. And then we have ablation. And ablation is a process that consists of like snow and glacier ice melt. So those are like two processes that run life of the glacier. And here on this graph, you can see here in the upper part, you got buildup of mass, which is accumulation, and then you got all this nice snow blanket. But in the summertime, the snow melts and also ice melts, and that's why this area to this red line is called accumulation area, and lower part is called ablation area. It does not mean that snow does not melt here, but in terms of persistence of snow, in the accumulation area, there's always some snow left, or there's no ice melt. And in the ablation area, all the snow melts during the summertime, and quite often also glacier ice melts out. And the red line between those two areas is called equilibrium line altitude. This is one of indexes that we use in glaciology to tell about glacier's shape. If it's when it's in a good shape, then equilibrium line altitude is quite low, and there's a pretty big accumulation area, and ablation area is small. And if this goes up line, this means that glacier melts out faster than it gains the mass. So at the equilibrium line altitude, annual mass balance is 0. So there's no mass gain, but there's also no mass loss. As I said, glaciers are like rivers of ice, and if a piece of ice does not move, then in glaciology we call it dead ice, and it's not considered as a glacier anymore. Very often parts of the glaciers are cut out by big crevasses or moraines, mostly during to melt out. And these chunks of ice, if they do not move, then they are not considered glaciers. And what's causing the glacier movement? Well, first of all, if they want to advance, so go forward, then we need a mass buildup, as there are two processes that run the glacier advance. One is ice deformation, and when you would have like more mass here, then all these ice crystals will move a bit, deform, and ice will start flowing. So with ELA decrease, we would have a glacier advance. ELA goes down and glacier goes forward. The other process is run by meltwater. So even with glaciers that have negative mass balance, so that they melt out, they will go forward, and it's due to forming a very thin layer of water under the glacier. That's the case of temperate glaciers, so glaciers that can be infiltrated by water. So during the ablation period, snow melts here on the surface, and ice melts here on the surface. And all this water, it can go on a glacier surface, but it can also penetrate the glacier, go down to the bottom, to the contact with the bedrock, and then form a very, very thin layer of water, which will push up the glacier, and then the friction goes down. There's less friction, and glacier will move forward much faster. So thanks to that, we can have a glacier advance. And if it's a cold glacier, which means there's no water in glacier body, the temperatures of the ice are much, much lower, then it's only ice deformation. So it's like clay. If you would have like soft clay and there will be a lot of that, it will just flow slowly down due to movement of crystals. And that's how it looks like. On the upper panel, you can see front of one of Icelandic glaciers, and the lower photo is taken 4 years later, and like for a scale, it's just a few meters. Here, from here to here, it's about 50 meters, but it's still slowly going forward, advancing. So even in a warming climate, we can have advancing glaciers, which is good, but most of them are unfortunately retreating. And here you can see that this big mass of ice carries also material. It's not only ice, all these dark layers here. This is rock material. This is also layers of Cryoconites, which I will talk later on. Lots of stuff going on. It's not just pure blue ice. Then, now we are with retreat, which is unfortunately more common to most of the glaciers in the world now. And it happens when ELA, which is ELA, it's increasing. which means that lower part of the glacier, it's, well, formally we call it movement, but formally it's not movement, it's melt out. As when ELA is decreasing, which means that there's less snow, there are higher temperatures in this part, and it's melting out. This lower part is melting out, and it's cold retreat, and it happens to most of the glaciers in the world now. That's how it looks in the Alps, and this is also five years difference and scale. This part is about 150 meters, even more, 200 meters. In 5 years, 200 meters of ice melted out in the Alps. In Svalbard, we have similar glaciers, maybe not that hanging, and they also melt out pretty fast. Well, Hansberg Glacier, which we've been monitoring for past 40 years. In these 40 years, has retreated for 2.5 kilometers, and it's a big glacier. Is it a problem, like vanishing glaciers? With this picture, you can see Pisol Glacier high in the Alps, and in 12 years, the volume of the glacier has changed by 60%, which means that if the meltout rate will still the same in 2026, 27, there won't be Pisol Glacier anymore. And that's the case for many glaciers in the world. It's not only tiny glaciers in the Alps. It's glaciers in the Arctic that are melting out super fast. It's glaciers in the Antarctic Peninsula that are melting out super fast. That's the case of glaciers in Pyrenees. A friend of mine works with glaciers in Pyrenees, and he told me that they won't have any glaciers in next 10 years. And why it's important to have them? It's not only they are beautiful, but in many places in the world, people depend on glaciers in terms of water, as glaciers are storage of water, especially fresh water. And if there won't be glaciers that accumulate water as snow during winter time and then act as water tanks in the summertime, there will be more droughts, and people will have to move from the places. Okay. And how is it? As I said, I'm a glaciologist, but for past few years, I also work with biologists, as it's really interesting to see what's happening in the ice and life. There's blooming life on the glaciers and ice sheets, but it's also, for most of these organisms, is living on the edge, living in extreme conditions. By extreme conditions, I mean during winter time, there might be no water. Might be, if it's in the Arctic, then it might be extremely cold and dark. There's no light during the polar night. Same with Antarctica, there's no light for half a year. And in the summertime, it can be extremely wet. There's no food, and there's still organisms colonizing the glaciers and ice sheets. This is a picture taken in Antarctic ice sheet. One of the extreme environments is bloodfalls in Antarctica, in McMurdo dry valleys. And this is, as you can see on the picture, this is a waterfall that flows out from the Taylor Glacier. And for many years, researchers were thinking, wondering from where does it take its color, and it wasn't clear till 10 years ago when NASA built, it was called a mole, and it was a robot that managed to melt into the ice and look for the source of this red water. And it appeared that there's a subglacial ecosystem, basically a subglacial lake under the Taylor Glacier, and at the top there's like this Taylor Glacier, and it's full of light. There's lots of oxygen, low salinity, low chloride, low sulfate, and very low temperatures. And under this blanket of ice, there's a hidden gem, which was isolated marine system. As 15,000 years ago, there was a sea, and some of the seawater got trapped by the glaciation, by advancing glacier, and it has formed kind of time capsule where bacterial ecosystem formed. Well, it was there, but it evaluated to completely new form. And those are conditions where there's no light, no oxygen, high salinity, high chloride, high sulfide, and still very low temperatures. So it's hard to get any energy. And this, as there's no photosynthesis, as there's no light, the microorganisms that live there can use organic and inorganic carbon for growth. And they actively cycle on iron, sulfur, and carbon. And this reddish color that we can see in the bloodfalls, in this waterfall that flows out from the subglacial ecosystem, it's mostly due to iron oxides. And it was really interesting to see, as for many years, a lot of researchers thought that it's just water that is fertile with iron, and it oxidizes when it goes to the glacier surface. But at the end, we learned that there's extremely specific ecosystem that lives under the ice. As this microbial life, those bacteria, they would not survive if they go out through the channels outside the glacier. Then they die, and we cannot find them anymore. The other example of, like, first we talk about life under the glaciers, but there are extremely big ecosystems forming on glacier surface, and they are called Cryoconites. As extremely big, I mean, on Greenland ice sheet, there might be belts of Cryoconites fields that are 30 kilometers wide. So there are areas with hundreds of square kilometers of Cryoconites. And Cryoconites, it's all these holes here, it's not one ecosystem. Each hole is a separate ecosystem, and it's formed with, first you got grains of material. This can be rock dust, this can be some soil that falls down on the snow, and then it absorbs energy, and little lake is forming around. And in this lake, bacterial and algae communities start to develop, and they start living in symbiosis. Temperatures, as the material is dark, it has lower albedo, so it absorbs more solar energy and does not freeze. And during the warm months, these areas are blooming. Like the effect of Cryoconites on glacier meltout can be extremely big due to change of albedo. And as I said, there can be millions of ecosystems like this. All these little dots here, they're like separate glacier microecosystems. But at the end, they can form big zones that affect, on one hand, the glaciers are a place to live for these little creatures. On the other hand, these little creatures, like these ecosystems, they destroy the glaciers by advanced meltout due to lowering the albedo. We're still with the life on the glacier surface, and this was when I was preparing for this presentation. This was really unexpected for me to find that there are organisms that spend all their life cycle. I mean, all their life in glacier ice, and they are called iceworms. And they are earthworm cousins. They look like little earthworms, but much smaller. They are up to 2 centimeters long, and they spend all their life in glacier ice, like in fern or in the snow, but still on the glaciers. They can be found in just a few places in the world, mostly on glaciers in Alaska, and they feed on material that is deposited on a glacier. I mean, like organic particles that are deposited on a glacier. Interesting thing is that during the summertime you can find them on a glacier surface as they are feeding, and during the winter time they go a bit deeper in fern and hide in these areas filled with air and bit of liquid water to survive there during the cold months. Another form that is kind of living on a glacier, those are also kind of ecosystems. They are called yoclamis, which is directly translated to glacier mice. First, they were found in Iceland, and it's the best place to look for them and study them. But they can be also found in Svalbard and Alaska. Yoclamis, which is like glacier mice, this is a mix of moss. Here on the top you can see all around there's a moss, and inside there are cyanobacteria, and they form kind of symbiosis. And funny thing is, they look like little hedgehogs, and they can move. it's not that this is growing on the ice. In most cases, they form around little rock, and all these moss and cyanobacteria start growing around the rock. And with high winds, they can roll. And very often you can see a lot of them moving like pebbles on a glacier surface, like in these pictures on left. It's not like those are like one and there's nothing. There can be a lot of them. Oh, sorry. And it's not the last one, but there's like many more of creatures living on a glacier. But there's a tiny bird which is called white-winged diuca finch. It's living in South America. And as they are afraid of predators, the place they found to be best for their nest is glacier fronts, which can be 30-40 meters high, like glacier walls. And these little birds decided that it's the best place to nest, even with extreme conditions like cold. Like if I would be a bird, I would rather prefer probably to nest on a tree. But as these are high mountains, there's no trees. And only place they could hide is this glacier fronts. So no predators will eat their eggs and later on little birds. And last creatures that inhabit glacier it's us humans, and this can be temporarily, like for 2-4 weeks, as we did years ago in Westfalna ice cap. We drilled for an ice core and stayed on the top of the ice cap for several weeks in a tent. This could be temporal shelters like Hans Cabina on Hansplan in Svalbard. This was a glaciologist laboratory in the 60s and 70s. But this could be also all year round manned stations like Amundsen's called South Pole Station, which is on the South Pole and people live there all year round. This could be Concordia Station in Antarctica, which is also all year round, or Halley 6 Research Station, which was all year round and now due to safety, it's used only during the summertime. So we humans are also capable for staying on glaciers for a long time, and in extreme conditions. But I would say that from all these creatures I've mentioned today, probably most extreme environment is the lake under the Taylor Glacier and Cryoconites. Well, I think that's all for me.
Watch other recordings from webinars on our YouTube channel, youtube.com/EDU-ARCTIC. EDU-ARCTIC 2. From polar research to scientific passion, innovative nature education in Poland and Norway receives a grant of 240,000 euros received from Iceland, Liechtenstein and Norway under EEA funds.